Hmm. Hi, everybody. Let's see if this is working. Okay, I'll use this one. So, hello. My name is Che. I'm from Northeastern University, and today I want to go through kind of a literature review on the topic of neural networks and clustering. This is not something that people talk about very often, which apparently is what I do. Just do things that most people don't talk about very often. And in neural networks, people tend to deal with supervised learning, and clustering is not exactly supervised. So, in any case, we're going to be going over, in general, three papers. One called Autoencoder based clustering by Song et al. Another one is by Tian, deep learning representation for graph clustering. And then the third one we're going to do is deep subspace clustering by G and Etal. And I don't think I'm going to follow the paper exactly. I want to do it so that, just so you guys kind of get the point of what they're trying to do. So, so like, it's not going to be exactly the same as the paper, but you guys will get the point. In any case, let's start. Like, in neural networks, right? Commonly, we have the type of problem where we have the input and we know the output. Like, we know the input, we know the output. What we want to find is this function that allows us to do the transformation from x to y, right? And we want to find this function. So, for example, the inputs could be like 0, 0, 0, 1. This is just an example. So with these kind of input and these kind of output, what we want to do is put these signals like 0, 0, right? 0, 0. We want to put it into some kind of black box neural networks. And we want to get the output to be 0. And over here, again, if we put 0, 1, we want to get a 0 as well. So in any case, here's the input, here's the output. And we want to find what's in here. So easiest way, which I'm going to assume you probably have seen this before. Let's say we put 0, 0 in here, is that to go through some kind of neural network. And the way it works is that we put whatever we have as this x1, right? We're going to put it into the network, which multiplied by w1. You can see it here. We put x1 in, multiply w1. And then we put this part in, and then multiply by w2, which is right here. And then lastly, well, not lastly, then you add them together, which is right here. Once you add them together, this whole thing is put through some function, which we call it the activation function. Activation function. This activation function then gives you the output here. And this activation function, H, could be in a lot of forms. It could be either this thing called a ReLU or something like a sigma. The exact function is not really the topic of this talk. The idea what I want you to get is that we don't know what W1 and W2 is. We want to find the W1 and W2, which then characterizes this whole thing that allows us to have this kind of behavior that we just talked about. So we don't know, like I said, we don't know W1, W2. W1, W2. However, we can just guess. We'll make some kind of guess. We'll set W1, W2 into something like random. We don't know what it is. We'll just pick one. Once we pick one, we just put x1 and x2. Like remember, there's x1, 2, 3, 4. There were 4 signals that we were talking about. 1, 2, 3, 4. See, it's at the top. So that designates which signal that we're talking about. So we don't know what W is, but we set W to be something. And then we just put the signal in. And we're going to get some other signal. Of course, this is the true result that we wanted. So 0, 0 would have been 0. But we're going to get something that's wrong. I mean, this obviously does not equal to this. if you just randomly pick the W1, W2. And we're going to call this the estimate. And the estimate is going to be horrible in the beginning, obviously, because we just pick W completely randomly. Similarly, we can do this for every single signal, all the way up to 4, right? So we have these estimate for the first one, all the way to estimate to the fourth one. And chances are none of them are going to be equal. There will be some kind of error. And the way we measure the error, a very common way is, well, we take the truth and subtract from our estimate and square it, so we make sure it's always positive. And this is essentially the first error. This is the second error, third, fourth. And if we add all of them together, you can picture as this is our total error. So it's the total error with the W1 and W2 that we have chosen, right? W1, W2. Okay, well, of course, you don't want to have to write this long thing. What if we have a lot of signals? So we'll compress them into the summation. So I from 1 to n, right? So in our case, n is equal to 4. So we keep changing the I and we keep adding them together. So that is pretty obvious. And of course, this part right here was the estimate. And with the estimate, we can rewrite it. Remember, the estimate follows this equation, h, which is some activation function, with the summation. So I'm just going to move this right here. So this part becomes this. In neural networks, we want to find like W1 and W2, right? We want to find the W1 and W2 that makes this error as small as possible. Or we can write it this way. We want to find the W1, W2 that minimizes this expression, which is equivalent to the error. And very often we solve this using this thing called stochastic gradient descent and this thing called the back propagation. And that's not the point. I'm going to also assume that you've either seen the gradient descent video that I have. Make sure you watch the gradient descent video. Also, it's one of the videos that I have shown. But the idea is very simple. You just take the derivative of this and keep going in the downward direction, and that will give you the smallest W1 and W2. Well, using the same idea, right, people started making it deeper and wider. So instead of just something very small like this, they started stacking them on top of each other. And when they start stacking them, it starts looking something like this. So they just get more and more layers, and this makes it deeper. And also, they can make it a lot wider, depending on, like, maybe you have a lot of inputs. If you don't have that many inputs, the inner layer could be very, very wide. Given it to be more and more larger, we can start simulating very complex f of x. Like, so this could be very complicated. And with the complex neural networks, we're able to essentially mimic what we're doing. Of course, now there's lots of W's, lots of weights. Only 2 of them, which I just showed you. Now we have to solve a lot of them. But the idea is the same. You know, it's a slightly more complicated and larger equation, but we can essentially use gradient descent and backpropagation to solve this. And the idea is also the same, like I said, that given x, we want to find f of x that gives us y. This has been the problem, right? This is the typical problem in neural networks historically, and it's called supervised. You know the output. The output is being supervised. You can kind of see it that way, and that we want to find f of x. So today we want to talk about a less traditional aspect of neural networks, something that's more unsupervised and unsupervised with deep learning. And specifically, Like we want to talk about deep learning and clustering, topics of clustering. So how can we do this, right? Well, in neural networks, we assume that we know the input and the output, both the input and output, X and Y. But we're going to now assume we don't know Y. No idea. Now, how do we go about solving this? This was the objective of neural networks that we were looking at. And if we don't know this, like we can't really solve it anymore. It seems difficult. So, yeah, how do we do this if we don't know why? Well, in clustering, we are often given some bunch of data here, right? Here's some data, and we wanna cluster to each other together. And in this case, let's say X is the data and Y is the clustering. This is going to be 0, 0, 1. So all the data that's 0, 0, 1 will go here. So X1, X2 belongs to this cluster. And this one is going to be 1, 0, 0. So this one will go here, like somewhere here. And then this one will be 0, 1, 0. So it's just a way to designate which cluster it belongs. And that is the Y, which we don't know, and we want to find it. Okay? You want to keep make sure you understand like what we are looking for. So yes, it seems like we need Y. We don't know why, but we need Y to solve this problem. So this is the topic of today, like deep learning and how we do clustering with deep learning. Like I said, people started making wider and deeper neural networks. And given all these layers, people start wondering if each layer, if it means anything. Like, for example, if we just look at this layer, does this layer, like if we just look at it after it's trained, what does it look like? Maybe there's something some kind of pattern we can see. So people started looking at each layer, right? And here's an example I found from K-Nuggets called Can Deep Learning Find the Perfect Date? All right, so this is just an example. It's not exactly the most accurate example, but I think from it we can get an idea of the point I'm trying to make. So what it showed was that it had like a picture of a person. And once you have a picture, and then the output is yes or no. Is it a perfect date? Or is it not? And then what they did is they look at the layers in between. And they want to kind of see if there are any patterns they can realize from these layers inside. So this is the example that was shown there. And if we look at the face of this person, we started noticing, well, each layer, that you can kind of combine different parts of this layer to form the next layer. And then combine different parts of this layer again to form the next layer. Remember, that's what exactly we're doing, right? Whatever the input is, we're kind of combining them, we kind of multiply them by some weight, and then combining them. They are actually, combination of this forms this, and a combination of this forms that. That's very interesting. Each layer finds components that forms the next layer. From lines, you form features of the face, and from that you can form the whole face. Well, another way to view this is that each layer is a different way of representing the data. So this right here, right, is a way of representing the face through lines. Of course, you'll need a lot of combinations of lines to form the face, but this is a way you can use lines to represent it. Or you can use parts of the face to represent a face. Of course, you need to combine them somehow to form the face, but the information is there. And lastly, over here is like the whole face. So each layer, you can see it as a way to represent the data. Like here, you can represent data. Now, if a layer is a way of representing the data, Well, what is one layer if it's like very small layer? Well, if we look at this here, this is a representation of data, but it's a very compact way of representing the data, right? So this is the idea, this idea of, with autoencoders. It's essentially what we want to do is have some kind of bottleneck that allows us to compress the data. But of course, we didn't know why. What we do in autoencoders is just we set the y to be the same as x. So that you can think about it, no matter how you compress the data when you go this way, the information included here must be sufficient so that you can construct the same data, because we set y to equal to x, right? So no matter how we compress this x, no matter how we compress it here, right? We want to make sure this f of x contains the same information that allows us to reconstruct the same x. And this right here allows us to do the unsupervised part. Because we didn't know why, we just set it to x. So in often literature, this part right here, it's called encoding. You're encoding the data into something smaller. And then to get the data back, we call it decoding. Because, well, you're decoding whatever was encoded. So the new objective function looks something like this. So remember, we have y as the truth, and then y hat as the estimate. What we want to do is we want the input and the output. So this is the input, and this is output. We want the difference between the input and the output to be as small as possible. Find the weights that minimizes, the difference between the input and the output. And once we have solved this, what we do is we take this layer and use this one. Give us a very compressed version of the data. And this autoencoder, this concept of autoencoder turns out to be very useful for clustering. In clustering, right, we have the data and we're trying to group them together. And very often there's a lot of noise. And what we do is this thing called the PCA, which does dimensionality reduction. It takes something that's high dimension and change it to something that's low dimension, so that when you do clustering, all these extra dimensions are removed, which very often is just noise, and you give you a better result. We can now essentially use autoencoders, right? We can now use autoencoders, and we'll use autoencoding and get a new set of data. We're going to call f of x. And then we just do k-means on it. And this would be probably the easiest way to do deep learning neural networks with clustering. Right? This is what I'm going to start off today. And I think that's enough for today's video. In the next video, I will start moving on to the next topic. But this will give you a general idea of what we're talking about. Anyways, I will see you in the next video.